Welcome back to our course, Fundamentals of Operating Systems, based on the text Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter Galvin, published by Wise Publishing. This is the second lesson in our study of threads, and we are going to pick up here with a little more in-depth discussion of parallelism. So let's begin. In general, there are two types of parallelism: data parallelism and task parallelism. Data parallelism focuses on distributing subsets of the same data across multiple computing cores and performing the same operation on each core. Consider, for example, adding the contents of an array of a certain size. Say the size is 12. On a single core system, one thread would simply add the elements from 0 to 11. On a dual core system, however, thread A running on core 0 could sum the elements of 0 to 5, while thread B running on core 1 could sum the elements of 6 to 11. The two threads would be running in parallel on separate computing cores. There's also task parallelism, which involves distributing not data but tasks or threads across multiple computing cores. Each thread is performing a unique operation. Different threads may be opening on the same data, or they may be operating on different data. Consider again our last example. In contrast to that situation, an example of task parallelism might involve two threads, each performing a unique statistical operation on the array of elements. The threads, again, are operating in parallel on separate computing cores, but each is performing a unique operation. Fundamentally, then, data parallelism involves the distribution of data across multiple cores, and task parallelism involves the distribution of tasks across multiple cores, as shown here. However, data and task parallelism are not mutually exclusive, and an application may in fact use a hybrid of these two strategies. Support for threads may be provided either at the user level for user threads or by the kernel for kernel threads. User threads are supported above the kernel and are managed without kernel support, whereas kernel threads are supported and managed directly by the operating system. Virtually all contemporary operating systems, including Windows, Linux, and Mac OS, support kernel threads. Ultimately, the relationship must exist between user threads and kernel threads as shown in this figure. Let's look at three common ways of establishing that relationship between user threads and kernel threads: the many-to-one model, the one-to-one model, and the many-to-many model. The many-to-one model, as shown here, maps many user-level threads to one kernel thread. Thread management is done by the thread library in user space, so it's efficient. However, the entire process will block if a thread makes a blocking system call. Also, because only one thread can access the kernel at a time, multiple threads are unable to run in parallel on multi-core systems using the many-to-one model. You do recall our conversation of only one process per core, correct? So regardless of how many cores are available, using a many-to-one scheme, many user threads to one kernel thread, limits the processing. Green threads used the many-to-one model. Green threads refer to a thread library available for Solaris system and adopted by early versions of Java. Obviously, in our multi-core world, it doesn't make much sense to use this many-to-one model because it's unable to take advantage of the multiple processing cores, which have now become standard on most computer systems. The one-to-one model shown here maps each user thread to a kernel thread. It provides more concurrency than the many-to-one model by not blocking other threads when one thread makes a blocking system call. It also allows multiple threads to run in parallel on multiple processors. The only drawback to this model is that creating a user thread requires creating the corresponding kernel thread, and a large number of kernel threads may slow the performance of the system. Linux, along with the family of Windows operating systems, implement the one-to-one model. The many-to-many model shown here multiplexes many user threads to a smaller or equal number of kernel threads. The number of kernel threads may be specific to either an application or a machine. An application may be allocated more kernel threads on a system with 8 processing cores than on a system with 4 cores. Okay, what effect does this design have on concurrency? Although the many-to-one model allows the developer to create as many user threads as he or she wishes, it does not result in parallelism because the kernel can only schedule one kernel thread at a time. The one-to-one model allows greater concurrency, but the developer must be careful not to create too many threads within an application. In fact, some systems may be limited in the number of threads a programmer can create. The many-to-many model, though, has neither of these problems. Developers can create as many user threads as necessary, and the corresponding kernel threads can run in parallel on a multiprocessor. Also, when a thread performs a blocking system call, the kernel can schedule another thread for execution. One variation of the many-to-many model still multiplexes many user-level threads to a smaller or equal number of kernel threads, but also allows a user-level thread to be bound to a kernel thread. This variation is sometimes referred to as the two-level model, as shown here. Although the many-to-many model appears to be the most flexible of the models discussed, it is difficult to implement. Also, with an increasing number of processing cores appearing on most systems, limiting the number of kernel threads has become less important. As a result, most operating systems now use the one-to-one model. A thread library provides the programmer with an application programming interface for creating and managing threads. There are two primary ways of implementing a thread library. The first approach is to provide a library entirely in user space with no kernel support. All code and data structures for the library exist in user space. This means that invoking a function in the library results in a local function call in user space and not a system call. The second approach is to implement a kernel-level library supported directly by the operating system. In this case, code and data structures for the library exist in kernel space. As we're talking about user space and kernel space, remember our conversation about the memory manager and how the operating system is taking a chunk of memory itself, and each process also has its own chunk of memory. And all these chunks must be protected from outside incursion from each other. So to repeat, this approach implements its kernel-level library from that operating system memory space. Invoking a function in the application programming interface for the library typically results in a system call to the kernel. Three main thread libraries are in use today: POSIX pthreads, POSIX, POSIX, Windows, and Java. Pthreads, which is the threads extension of the POSIX standard, may be provided as either a user-level or a kernel-level library. The Windows library thread is a kernel-level library available on Windows systems, and the Java thread application programming interface allows threads to be created and managed directly in Java programs. However, because in most instances the Java virtual machine is running on top of a host operating system, the Java thread application programming interface is generally implemented using a library available on the local system. This means that on a Windows system, Java threads are typically implemented using the Windows API. Unix, Linux, and Mac OS systems typically use pthreads. For POSIX and Windows threading, any data declared globally that is declared outside of any function, are shared among all threads belonging to the same process. Because Java has no equivalent notion of global data, access to shared data must be explicitly arranged between threads. In the balance of this section of the book, our authors go into some detail about basic thread creation using these thread libraries. Although I won't be covering these narratives in this discussion, it will be worth your while to examine them carefully. In fact, I believe this will complete our unit on threads. So, let's take a break, review our notes, take care of any assignments you may have, and when you're ready, come on back and we'll move on to the next unit.